So, good morning, everybody. I just switch Tatooine, which is a nice place, of course, but we will need the whiteboard today or flip chart. So, hello. The first thing I would like to just remind you of today is that we have a book, which is quite a good book. It's a world standard for engineering students, more or less, for electromagnetics. Magdi Iskander. This is the 8th edition. Currently there is even the 9th edition, but the 8th edition is good anyway. And this book, first, is well written. Second, I recommend it to you. And third, we have bought plenty of those books for you, so that you can borrow that in the library. The university library has 100 pieces, so it's well enough for anybody who wants to study this subject. So if I can recommend you a book, this is the book that is for you. So this is one of those books. I will show you another book next week. And after all, heavy book or not, we will continue with electromagnetics. Well, I hope that you have found on YouTube our last lectures, which have been recorded and put there. If you do not know the location, a good idea is to go to the Moodle of the subject. Each subject at the Faculty of Electrical Engineering has its own Moodle page, and you can find there a link to the group where you can find lectures, but you also can find there a link to the lecture itself. So please use my resources that are available to you, like books and videos. Well, but anyway, after organization start, we would have to start with electromagnetics, which is much more important and much more interesting. Last time we have been discussing electrostatic field. We have learned that there is something called field strength. This field strength is in conjunction with field density, which is then in conjunction or in a mathematical relation, so that we can, in linear homogeneous and isotropic media, have a constant which links electric field strength and electric field density. And then we have used some small laws and calculations. The last thing we have done, as far as I remember, is establishing potential field strength in a stratified media. I mean, there was a ball immersed in another ball out of dielectrics, which then has been residing in a full empty space. And that was our last picture. Now, I would like to draw your attention to another kind of field, which is caused mostly by electric field, but this field happens in the case where the charges are not fixed and the field can cause their movement. Once you have a charge, let's say an electron, E, we remember electron is something which has a very small negative charge. So if you now have electric field strength from some other source that you apply on the electron, let's say this is the external field, E, well, the electron would move if it can. So if it can, it will start moving. And you know, as its charge is negative, it would move against the field line of the electric strength. So we have one electron. That's a very small charge. Now if you have an area with more electrons, with more charges that can move and apply electric field strength on it, that you get, you gave a birth to something which is called electric current. It is a transport of electric charge. Once many small charges begin to move, the result in the microscopic world is called electric charge. So this charge is more or less the thing we would study now. First, let's define quantities. We already have voltage, which has the same meaning here and in electrostatics. So let's just mention it. Then we have a new quantity, which is called electric current, I. And the electric current says, or denotes the amount of electric charge that passes the cross-section of the current path within a second. Or we can define it differentially, like the I is delta Q over delta T. So if we divide the electric charge that has passed the cross-section of a conductor and the time in which that has been done, we will get electric current. And if we want to make it very precisely, then we can limit delta to 0 with the exception we noted at the beginning of the course. But now we have current. So there is current, there is some charge flowing from one place to another. Like in electrostatics, where we had electric flux, we would possibly more tend to study the density of the flux. And this flux density is called current density, J. It is a vector, and we can find electric current I using an integral over a surface through which the current flows, and there would be the integrand would be the current density J multiplied by the surface element of that surface. So this is the a kind of definition of the current and flux density, which is called current density.
Excuse me, sir.
Yes?
Can you use a black pen instead of green pen? Because it's not
Yes, I will. Just a moment.
Thank you.
Now, is this better?
That's perfect.
Okay, fine. So now, we have a flux that flows through some surface. The density at that surface at different points is called electric current density, and we have the total flux, which is called electric current. Still, we are talking about electric charge, which movement is the current. Now, we have already learned about something which is called Ohm's law. I'm convinced that you have heard that during your previous education. But let us watch the Ohm's law in two different notations. The first is something you have possibly seen, and that something says that the voltage on a circuit is a product of a current and a resistance. So we have a resistance which opposes current, or is a voltage V over the resistor, and a current I flowing through the resistor. So this is something we have here, and this is the classic integral definition. We do not explore what is inside the resistor. We just have the integral value, which is the total current flowing through the resistor, and we have the integral value, the total voltage over the resistor. Now this is the formulation of the Ohm's law, which is called integral. We can also watch a small piece of the resistor, a small piece of the current inside, and such a small piece of the current would be described by another formulation of the Ohm's law, which is called the Ohm's law in a differential form. And this notation looks like this. We have the current density J, it's a vector, and this current density in the linear homogeneous stationary isotropic media is directly proportional to electric field strength. And the constant for proportionality is described like sigma, or some books describe that by gamma. Anyway, the unit of that is Siemens per meter, and this constant describes the ability of the material to conduct electric current. Now let's watch this equation again a little bit. We have an equation that says that there will be current density caused by electric field strength unless the conductivity is zero. Well, this is something that a little bit changed my view on electric current I brought from the basic education. I meant that the current is when you take a wire and short circuit the battery. Then you have a current flow from one pole of the battery through the wire to the other pole. But in this notation there is nothing about wires and nothing about a complete circuit. It only says that if there is field strength and some movable charge, there will be current density and therefore current. Now this looks strange, but it is a very important view because, for example, if you have a high voltage line, a very high voltage line, something of 200 kilovolts, 220 kilovolts, or 440 kilovolts, those are the values used in this country, you would be passing under it, and if there is not much noise, you could hear something which is called silent discharge. So there is a discharge on the surface of the line, but you are walking under it and you can easily know that the current is not flowing through you, you would learn. So there is some discharge that happens only around the conductor. Because there is high voltage on it, and because the field strength around the conductor is very big. By the way, this is a step back to electrostatics, but let us investigate for a moment the situation around this high voltage line conductor. So we have the high voltage line conductor, and it has some radius, let's say A. And as we know, the charge that is deposited on the conductor causes electric field strength around it. We have analyzed that in our first lecture. The electric field strength E is proportional to the charge density per meter tau and inversely proportional to 2 pi epsilon r. So, in fact, the field strength decreases with the distance. We don't like the silent discharge because it makes noise, it causes radio interference at short waves, it is a matter of accelerating ions around the wire, and those ions then bump the surface of the wire, so it degrades the surface of the wire. So, and after all, if there is noise, if there is some small heat, and you add that over kilometers of the line, you get some losses. So we don't like it. We would be able to get rid of it if we increased the diameter of the wire, because then the electric field strength is decreased, and once it falls under the maximum strength which the air is capable of bearing without destruction, without discharge, there is no more any silent discharge. Well, on the other hand, you can't make the power line with a conductor of this size. I mean, you would need a lot of copper or aluminium. You would also need a very strong mast that should be positioned each several meters to bear the heavy line. So that's not a possibility you would undergo. Is there any other option to decrease the electric field strength? Well, yes, it is. And it's used. And this is why the power line has in cross-section in Europe, for example, 3 wires. Those are 3 wires that are connected together. At some distance you can see connecting elements. So this is a one potential, but the electric field is not as good. This is not as good as it would be if there was one massive thick conductor, but is somehow weaker, and this reduces the electric discharge. Now, 3 conductors are a very poor approximation of a big circle, but anyway, in America only 2 conductors are used, and still it massively reduces the silent discharge. So this is about the line of high voltage. Now you would get anywhere electric current once there are movable charges, so the specific conductivity is not zero, and there is a strength that causes them to move. Now, as to a discharge and electric circuits, we are very happy in the way the nature is organized, at least in electric current fields, because we have two distinct and very different kinds of materials. We have a kind of materials that is called conductors. Mostly you can count as conductors metals like iron, copper, aluminium, gold, silver. You can also count as conductors a lot of organic materials like, for example, coal, carbon, and their specific conductivity is quite big. This conductivity, in fact, tells you what would be the conductivity of a cube made of that material, 1 meter by 1 meter by 1 meter, then connected to the circuit at opposite sides. So if we have the conductivity of this, we would, for example, get for copper 5.7 multiplied by 10 raised to 7th order Siemens per meter. So this is the conductivity of copper, and most metals have more or less similar conductivity. It's quite a good conductivity when compared to non-conductors, like, for example, plastics, glass, rubber. And the very nice thing about that is that the conductivity of insulators may fall to some 15 orders of magnitude under the conductivity of conductors. Why this is important? Well, because if that was not the case, we would not be able to make current flow only through the place we want, but we would be a part of the electric circuit anyway. So if we have a conductor with an insulation, in fact we can count on the situation that there is no current leakage, so that the electric wires that feed our light at the ceiling do not leak current to our bodies. So this is very important and a nice situation. This is nothing similar to electrostatics. I mean, the range in which permittivity of nature materials, well, the range of permittivity of nature materials is under 100 times the permittivity of vacuum. Well, the same would be for magnetic materials, a little bit better, but anyway, again, we can quite easily guide electric current. It is not easy to guide magnetic flux, and it's quite uneasy to guide electric flux. But fortunately, the electric current is that something which is most dangerous to a person. So we are able to handle electric current and to direct it through conductors where we want. And this is given by the big range of specific conductivity, which ranges from a huge number for example, copper, to a very small number for example, glass, silica, but even dried wood or plastics. Now there's a short time for questions. as I can't see any questions in the chat, I can't hear your questions, we would have to go on a little bit to investigate the field. So, yes, we have the basic equation, the Ohm's law in the differential form. We have now some other points, but let us first have a short thought about the nature of the steady electric current. The word steady is very important. It's like electrostatics. The field has been there everywhere and would not change at any time. That's the real nature of electrostatics. And the word steady current means that the current is flowing from the Big Bang to whatsoever. And now, if you have this situation, and you, for example, form a closed surface, a ball, an irregular ball, for a steady current case, it must hold an important point. If the situation is steady, you can't just create charge inside the ball and still create the charge and still drag it out of it, because such a situation would result in a big difference or would result in a big field density, electrostatic, and would drag the charge back. So if this works for a long time, you can't borrow any charge from inside of the ball. That means that any charge flowing in must flow out, and any charge flowing out must first flow in. And therefore, you can say that the total sum of charges flowing in and out must be zero. Or you could tell that the integration over a closed surface should of the charge density multiplied by the element of the surface of that ball must always be zero in electrostatics, which also could be expressed in another way. Divergence of the current density is zero. Well, having this in mind, we can say, okay, we have something which is quite similar to electrostatics. And then it follows that if it's similar, there should be similar equations. Now this is called analog, and you might be surprised that many years ago we had two types of computers. One of those computers were digital computers. This type survives, so you have that in your mobile phone, in your PC, in your laptop. But there were also computers that were not digitalized. They were working on continuous amounts of electric field and current, analog computers. And that idea was based on the fact that you can create an electric circuit which is governed by the same equations, I mean integral or differential equations, like another problem, for example from economy or from mechanical science. And due to the fact that at those times digital computers were quite slow, solving the problem by setting up a circuit was much faster. Well, but anyway, this principle could be used, for example, to find a parallel between electric current field and electrostatics. Why would we do that? No, well, because we already know how to solve electrostatic field. So if we find a set of similarities, we could possibly use that for solving electric current field. Now, in fact, what I'm going to prepare for that is a vocabulary. A vocabulary basically is a double column set in which you have two columns. One is in one language, for example Czech, the other is in another language, for example English, and you can find equivalents. So, for example, in Czech there would be pero, and in English there would be pen. And you can say, okay, whenever I want to translate the text from Czech to English, I will replace pero by pen. Whenever I want to translate the text from English to Czech, I will replace pen by pero. Simple. And what about electric current field? And electrostatics. So, well, in electric current, the total value of electric current is called electric current and denoted I. In electrostatics, the important quantity is charge, Q. Okay? I've already told today that we have something which is of the same value and meaning in both fields, and it's called voltage. Now, we have something that is a ratio of those two values in the electric current field. So, if we divide voltage over current, we get resistance. Or as a division of current against voltage, we got conductance. Well, okay, if we divide the same values here, we get capacity. Here there is no meaning, but this is capacity. And we will talk about capacity later today. Well, okay, we had a value that was called the density of electrostatic field, and we denoted it by D. And we have the density, which is in, sorry, I mixed English and Czech part in the vocabulary. We have the density, which is current density J, and we had in electrostatics the density of the field, which is flux density D. Now, for example, we have a set of values in this and this part. Now, we have the same for voltage, which means that for the potential phi, we have the same word in both current field and electrostatics. And just having those several points, we can now derive more similarities. For example, we have the Ohm's law in differential form, which says that current density is conductivity multiplied by field strength. Well, we already have this and this in our vocabulary, do we? Well, we had the voltage, so we have, if the potential is the same, then the field strength must be the same in both words. And now we would find another pair of values. If this is true, and we have another definition here, which is D is proportional to E with the constant epsilon, I mean electric flux density is proportional to electric field strength, where the proportionality constant is the permittivity. We now know that we could substitute conductivity in this field and permittivity in the other. Now we have a table which can be used to translate equations, and that is something we will do, but we will make a short break now, and then we will first start with a property that is called capacity, and then change it to a property that is called conductivity, conductance, and so on. But we have the right to have a 5-minute break now, so please, your questions now or your questions 5 minutes later. So after the break we will start exactly here, and I will read the chat and I will expect your questions. So 5 minutes later, bye.